Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, Tifr, Jest, IIT-Jam and other exams related to physical science. Okay. So this is the fifth part of the series of CSIR NET Physics 2021 paper solution. Okay. So let's before starting the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, and also guys, I would request I would request the students, please share my details with your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay, so let's get started. So this is the fifth part of this series of CSIR NET Physics 2021 paper solution. Okay guys, so question number first is, a two-state system, a two-state system, evolves under the action of under the action of the Hamiltonian H equal to E naught cat A into bra A plus E naught plus delta cat B cat vector B plus bra B. Okay, where cat A and cat B are its two orthonormal states. Are to its orthonormal states. These states transform transform to one another under parity that is P when operates with A, that becomes B, okay, state B, and parity P when operates with B state, it becomes state A. Okay, if at time t equal to 0, if at time t equal to 0, if at time t equal to 0, the system is in the system is in the state system is in the is in is in a state is in a state is in a state is in a state of definite parity, state of definite parity, state of definite parity, p equal to 1. Okay, the earliest time, the earliest time t at which the probability of finding the system the probability of finding the system in a state finding the system in the state finding the system in the state of parity, state of, very good question guys, okay, state of, and tough question, the system is in the state of parity p equal to -1 is 1 is okay. Options are, option number A is pi h cut upon 2 delta. Option B is pi h cut upon delta. Option C is 3 pi h cut upon 2 delta, and option D is 2 pi h cut on delta. Okay, so this is the question guys. Meanwhile, just let me check. Okay, so this is a very good question, and I'm going to read it again. Okay, I'll explain the question and then I'll solve it. A two-state system. So we have a system who has two states. Okay, evolve. Okay, that is, it evolve under the action of Hamiltonian, and Hamiltonian is given guys, that is h equal to E naught cat A bra A plus E naught plus delta cat B bra B, where A and B are two orthogonal states, or these are two. Okay, these states transform to one another. Okay, these we can change these states to one another. Okay, under the parity. Okay, that is given PA. If you operate P, that is parity with A, that becomes B, and if we operate parity with B, that becomes A. Okay, so these states transform to one another. Okay, if at time t equal to 0, the system is in a state of definite parity p equal to 1. So at t equal to 0, system is in a definite state. Okay, the system is in definite state whose parity is 1, that is given. Now what we have to find is, we have to find the earliest time t. Okay, the earliest time t at which the probability of finding the system in the state of parity p equal to -1 is 1. Okay, the probability of finding parity is p equal to -1 is 1. Okay, okay, is 1 is okay. So we need to find that time for which the probability of finding system in the state of parity p equal to -1 is 1. Okay, that time we need to find it, guys. Okay, so now I will explain. Meanwhile, just let me check whether I'm audible or not. Clarity P
Yes.
equal, yes, I'm audible, so I'll proceed further. Okay, so we need to find the time. Okay, we need to find the earliest time, okay, at which the probability of finding system in the state of parity P equal to -1 is 1. Okay, so let's get started. Okay, so first we'll write whatever we have been given. Okay, so we have been given, that is H is given, Hamiltonian of the system. Okay, that is given, of the system is given, and that is epsilon 0 at A into bra A. Very good question, guys. Okay, and that is epsilon 0 plus delta get B into bra B. Okay, so this is the question which is given. Sorry, my apology, it's the Hamiltonian given. Okay, this is the Hamiltonian which is given. Okay, because this is epsilon 0 cat A bra A plus epsilon 0 plus delta cat B bra B, right? So we can write this into in matrix form, guys. If we have this type of Hamiltonian, so how to write this in matrix form? Okay, in matrix form, this is going to be in matrix form. In matrix form, this H is going to be simple, guys. This will be E. Okay, E naught 0, and this is 0, and this is E naught 0, and this is 0, E naught plus delta. So this is the matrix form of Hamiltonian. This is very important step, guys. Okay. Okay. Given by, that is H minus lambda I, right? This is the, that is going to be equal to 0. So H we have this, right? So this is going to be, if you write this, this is going to be epsilon 0 minus lambda 0 and 0 into E means this is E0. Okay, E0 plus delta, E0 plus delta, E0 plus delta minus lambda equal to 0. Determinant of this equal to 0. Determinant of H minus lambda equal to 0. So we'll solve it. So this is going to be E naught minus lambda into E naught plus delta minus lambda equal to 0, right? So from here, value of lambda, that eigenvalues are E naught comma delta plus or E naught plus delta. Very simple thing. Okay, E naught plus delta. This is E naught. Okay, E naught plus delta. So these are the eigenvalues. So we have got eigenvalues, right? Lambda value means E we have got. Okay, so simple thing. Now what we are going to do is now we'll find the eigenfunction of the system. Okay, eigenfunction of the system. So eigenfunction of system is going to be, this implies eigenfunction eigenfunction of the system, eigenfunction of the system, eigenfunction of the system is given by that is going to be this one, phi. We can write phi, which is function of t. Okay, that is going to be equal to, we can write eigenfunction. So we have got eigenvalues, right? So we can write the eigenfunction of the system, and that is going to be cat A e to the power minus I E naught I E naught T upon H cut and plus at B. These are the eigenstates, right? These are the states, and so this is going to be eigenfunction is going to be e to the power minus iota E naught plus delta E naught plus delta E naught plus delta upon H cut into T. Okay, so this is one. Okay, so this is the eigenfunction we can write, because we have the eigenvalues, that is E and E plus delta, right? So eigenfunction which is function of T, that is going to be eigenfunction that is phi T, right, at time T, that is going to be this one, cat A e to the power minus iota E naught T upon H cut plus cat B e to the power minus iota E naught plus delta upon H cut T. Okay, now according to question, we have been given that parity, right? We have given, according to question, we have according to question, we have that parity operator given, right? Pi, if you operate pi with pi, which is function of T, that eigenfunction, right, it will give minus pi, which is function of T. Okay, this is given because in the question, right? This one we need to find if at time T the system in this one, the earliest time at which the probability of finding the system in the state of parity P equal to minus 1, right? This is given, so this is going to be minus T, right? Or we can write a very important thing, guys, or we can write here pi, this is the pi value, right? Pi, this is parity operator A e to the power minus iota E naught T upon H cut plus pi B e to the power minus iota e to the power minus iota e to the power minus iota E naught plus D E naught plus dt E naught plus dt upon H cut, my apologies, it's delta E naught plus delta T, and that is going to be, so we are operating this with pi, right? So this is going to give minus pi, right, according to this, because parity is given minus 1. So this is going to be minus A operator minus A e to the power minus E naught T, minus B e to the power minus iota E naught plus delta T upon H. Okay, so now this operator, we know, if you operate with a pi, that is parity operator, it changes a state into B, right? This is given in the question, so we can write in next step. This we can write it pi. We operated with this parity with A, means this will become B. So this is going to be very important step. Okay, so B, get B e to the power minus iota e to the power minus iota E naught T upon H cut E naught T upon H cut, and plus here this is we operate with parity is operating, we are operating this parity with B, means this is going to be A, right? According to question, this is given, so this is going to be get A e to the power minus iota E naught plus delta T, E naught plus delta, E naught plus delta, and outside T upon H cut, T upon H cut, okay, and that is going to be equal to this one, minus A and minus B, right? Minus A e to the power minus iota E naught T upon H cut minus B e to the power minus iota E naught plus delta T upon H cut. Okay, so this is what it is going to be. Okay, this is important step, right? Now what we can do is we can this we can call it as equation 1, and now what we can do is we can compare the coefficient of A and B. Okay, so this is coefficient of A and B, right? This is minus, and this is minus B. Okay, so now we'll compare the coefficient of A and B. Okay, comparing coefficient of A and B. Okay, so this is going to be for A. First we will compare for A. Okay, coefficient of A. So coefficient of A is this and this, right? This. So this is going to be, coefficient of A is going to be e to the power minus iota E naught plus delta T, this one, upon H cut, that is going to be equal to this one, minus e to the power minus iota E naught T upon H cut. And for B, comparing for B, so this is going to be for B, this is also we are getting the same, that is e to the power minus iota E naught T upon H cut equal to minus e to the power minus iota E naught plus delta T upon H cut, right? Both are same, guys. Just we can write, we can take minus here and we can take this side, right? So both are same. So both are same means that implies both are same. Okay, so we can see both these conditions are the same. Okay, these are same. So since both these conditions are same, so it means this either this will be equal to this or this will be equal to this. We can take any one, right? So it means e to the power minus e to the power minus iota E naught T upon H cut, that is going to be equal to e to the power minus iota E naught plus delta T upon H cut Okay, so now, or we can write this one this is going to be, we can take this side, right? And so this is going to be like this. So we can write we can write like this. This is going to be e to the power minus iota E naught plus delta T, and this is going to be upon e to the power minus iota E naught T plus H cut, that is going to be minus 1, and this minus 1 value is equal this is like this, right? Or we can write, if we take this upside and then faces are same, and in that case this this is minus, guys. Okay. Yes. So it will go up and it will become positive. So this is going to be e to the power iota delta t e to the power iota delta t upon h cut that is going to be equal to e to the power I pi, because I pi, because e to the power I pi value is minus 1. E to the power I pi, that value is minus 1, right? So from here we can write delta t upon h cut equal to pi. Delta t upon h cut equal to pi. Delta t upon h cut equal to pi, right? So it means delta t upon h cut equal to pi. So from here value of t is going to be that is pi h cut upon delta. So this is the answer. Okay. So which option is matching, guys? Let me check which option is matching. Option B is matching, guys. Okay. Pi h cut upon delta. Okay, so this is the answer, guys. So very good question. I would request you to practice it, guys. So it's a good question. Okay. Okay, so this is the answer. Next question we are going to solve. Next question is question number 2. This is also a good question from Electrodynamics. Okay. So question is, a conducting wire in a shape of conducting wire in the shape of a circle conducting wire in the shape of a circle lies on the xy plane with its center at the origin okay. A conducting wire in a shape of circle lies in xy plane with its center at origin. Okay. A bar magnet a bar magnet moves with a constant velocity a constant velocity towards the wire towards the wire towards the wire towards the wire along the z-axis. Okay, along the z-axis as shown in the figure below. Okay, as shown in the figure below, as shown in the figure below, as shown in the figure below. Okay, so I'll make a figure diagram. Okay, so this is a loop, circular loop. Okay, it's a circular loop, guys. And this is the center of circle, which is origin. Okay, and we have the magnet. This is a magnet we have. Okay, this is south pole and this is north pole. Okay, south pole and north pole. Okay, and this is along moving along z direction. Okay, so this is the z direction, guys, plus z direction. Okay, and here we have observer. This observer facing the ring. Okay, observer facing the ring, ring, observer facing the ring in the direction of arrow. Okay, so this is the figure given. Next, I'll explain this question also. Okay, so we take t equal to 0 to be the instant at which the midpoint of the magnet of the magnet midpoint of the magnet the induced current to be positive when it is counterclockwise, when it is counterclockwise counterclockwise. Counterclockwise means anti-clockwise direction. Okay, counterclockwise as viewed by as viewed by the observer facing the loop, okay, and the incoming magnet incoming magnet. In these convention, in these conventions, in these conventions, the best schematic, the best schematic, representation, schematic representation of the induced current, of the induced current, of the induced current, I, which is function of t, which is function of t as a okay, yeah, it as a function of t, as a function of t is, okay. So options are given, I'll explain it, okay. I'm writing question first. So options are, so we have to choose the correct graph, okay. Okay, so number A in the graph is given like this. This one, this graph B, graph C. Okay, so I'll make that only this graph A. Next page I'll make. In graph A, this is given like this, okay. This is the graph A. Not taking exactly, so I'll make like this. Okay, this is graph A. Graph B is like this. Okay. This is graph B. Next, C is given. Like this. Okay, this is this graph C. and graph D is these are schematic representation, and we need to check select the correct one. Okay, so this one is like this. Concept based question. This is the graph, guys. This is the graph. Okay, so these graph are given. So now I will explain the question. Okay, so question is this one, guys. A conducting wire. So we have a conducting wire in a shape of a circle, which is in a shape of circle. Okay, lies on the xy plane with its center at origin. Okay, a bar magnet moves with constant velocity towards the wire along the z direction as shown in the figures. Okay, so this is the circular wire in xy plane. Okay, and there is a bar magnet which is moving along the z direction of the loop. Okay, and this is the north pole, and this is the south pole of the bar magnet. Okay, here is observer. Okay, observer is facing to the ring in the direction of arrow. Okay, so there is a observer. Okay, now we take t equal to 0 to be the instant at which the midpoint of the magnet bar magnet or magnet is at the center. Okay, that is the condition given. Now the wire loop and the this one, this is we take t equal to 0 to be the instant at which the midpoint of the magnet is at the center of the wire. Okay, and the induced current to be positive when it's counterclockwise as viewed by the observer facing the loop and incoming magnet. Okay, and in this one. Okay, so in this convention, the best schematic representation of induced current as a function of t we have to select. Okay, so which will be the best representation, and these are the graph I versus t. Okay, current versus time, I versus t. This is also I versus t. I versus t. Okay, I versus. So here, guys, very important thing I'm going to explain. Very simple question, concept based question. Okay. So and the direction of current is clockwise, guys. If we see from the right side. Okay. So now I'm going to solve it. So guys, you need to understand here so this is the magnet which is moving towards this loop. Okay, and because of that this circular loop there would be current will get induced. Okay, current will induce in this loop, and the direction of this current will be this clockwise direction. Okay, this is clockwise direction if we see from the if you view from the right side. Okay, so the direction will be that this one. So direction will be, because the north pole is moving, approaching towards the wire or the loop, right? So the direction of the induced current is going to be to the uh, to the uh, to the clockwise direction. Okay. Now what will happen is, and also guys, if the direction of the loop, the direction of the current in the loop will be is in negative direction, I mean to say counterclockwise direction, okay, or we can say the anti-clockwise direction, okay. In that case, the induced current is going to be negative, okay. Sorry, in anti-clockwise direction, induced current is going to be positive, and in this if in this because in this case the direction of current is in clockwise direction, so in that case it is going to be this one negative, okay. So now I'll explain it. I'll write it, okay. As you need to understand, it's a conceptual question, guys. I'll explain it, okay. As north pole of the magnet as north pole of the magnet moves towards the coil okay. This is important thing, okay. Moves towards the coil, the induced current the induced current must flow in the direction direction clockwise, okay. That should be clockwise direction, okay. As seen from the right, as seen from the right. This is what shown in the figure as well, you can see, right. From here it is clockwise. Next, yeah, so the induced current must flow in the direction which is clockwise from the right, okay. Must flow in the direction to create north polarity on the left, okay. Create north polarity on left okay. However, so direction must be in the clockwise direction from the right, okay. So that to create the north polarity on the left, okay, because north pole is approaching towards the loop. Next, however, the current seen from the right, the current seen from the right, current seen from right, and flowing counterclockwise is to be considered positive. I have already told you, right? So this one. However, the current seen from the right and flowing counterclockwise is to be considered positive, and that should be positive, guys. At this time, the current is negative, guys. Okay, because the direction is clockwise. If direction will be counterclockwise, or that is anti-clockwise, then the the current should be positive. Okay, should be considered positive. Okay, current will produce this current. This is a positive. Then this current will produce this current will produce a south polarity, a south polarity, a south polarity on the left of the coil, on the left of the left of the coil, on the left of the coil. Thus, we can see, thus, as seen by observer, as seen by observer, as seen by observer from the right, the current must flow clockwise. The current must flow clockwise to produce north polarity on left. Okay, to produce north polarity on the left, because in left hand side north is approaching, right? Okay, so this clockwise current will be negative, of course, right? So this clockwise current, this clockwise current will be negative, thus as the bar magnet approaches the coil, as the bar magnet approaches the coil, okay, goes towards the coil. Okay, the induced current will be negative, the induced current will be negative, induced current will be negative, and after it is about to cross, after it is about to cross, after it is about to cross the induced current must be positive. So what it is saying is, here you can see this one. So the induced current direction is clockwise, and the induced current will be negative. Okay, so it will be negative as it will approach to this loop, and but it is so what will happen is, when it is about to cross the loop, when this magnet is about to cross the loop, in that case, this one. So in this case, the as the bar magnet approaches the coil, the induced current will be negative. Okay, and after it is about to cross the loop, the induced current must be positive. Okay, so first the current will be negative, and after some time, when it is about to cross the loop, that time this will be positive. Okay, so this means which graph is going to be the correct option, which will be the correct schematic graph, and that will be option D, guys. Okay, this option D. Okay, this one, and this is the answer, guys. Option D is the answer. Okay, so this is a very good question, guys. Conceptual question. Okay, so first the here. Okay, so first it will be negative current. Okay, and direction is clockwise, and after some time, when this magnet is about to cross this loop, that time it will be positive negative. That means the this option B graph, this graph will be the best representation, best schematic representation. Okay, so this is the answer. Okay, guys. So this is the one. Okay, guys. So today will be one question. So let me just check one more question I'm going to solve. This is also a good question, so I'm going to solve it. Okay. So next question is, question third. This is a vector potential. This is a very good question. Okay, and formula based. The vector potential, the vector potential, conceptual based question. Okay, potential, the vector potential for an almost point-like magnet, located at origin is A equal to mu sin theta upon 4 pi r square phi cap. Okay, where r comma theta comma phi denote the spherical polar coordinates. Okay, denote the spherical polar coordinate. spherical polar coordinates, and phi is the unit vector along phi cap. Okay, a particle of mass m, and charge q moving in the equatorial plane. Okay, equatorial plane of the dipole. Dipole starts at time t equal to 0 with initial speed v naught, and an impact parameter b. Its instantaneous speed at the point of closest approach is. Okay, option are option A is v naught, option B is 0 by 0, option C is v naught plus mu q upon 4 pi mv square, and option D is root v naught square plus mu q upon 4 pi mv square whole square. Okay, this is the question. Okay, very good question and conceptual question, guys. Okay, simple question. So question is the vector potential for the almost point-like magnet located at the origin. Okay, vector potential of the almost point-like magnet which is located at the origin is given. Okay, A equal to U mu sine theta 4 pi r square theta phi cap, right? Where r theta phi denote the spherical polar coordinates and phi is the unit vector along phi cap. Okay, and a particle of mass m and charge q moving in the equatorial plane of the dipole. Okay, starts at t equal to 0 with initial speed. Initial speed is v naught. Okay, and the impact parameter b, its instantaneous speed at the point of closest approach. Okay, at the point of closest approach, its instantaneous speed we need to find. Okay, very simple question. Okay, so I'll explain now. So guys, this is the origin. You need to understand. Okay, this is the origin, and at this point-like magnet is placed. Okay, and this is the equatorial plane of this dipole. Okay, this one, equatorial plane. So at some point here there is a particle of mass m and charge q which is moving with initial speed v naught. Okay, towards this dipole. Okay, now because this is a dipole, right? And just wait guys. Okay, okay guys, so this is a dipole, magnetic dipole, right? So there will be effect of magnetic field on this particle, right? So now because of this effect of magnetic field, what will be the speed of this charged particle? Okay, which we need to find at the point of the closest approach. Okay, so very simple guys, very simple one. It is the conceptual question, so you need to know this concept only. Okay, so because dipole is placed at the origin, right? So it is not moving, means there is a static magnetic field, magnetic field, right? So I'll write this. So it means a static magnetic field. This concept you need to know. Okay, a static magnetic field, a static magnetic field, static magnetic field doesn't alter, doesn't or does not alter, does not alter, does not alter, does not alter the magnitude of, alter the magnitude, magnitude, the magnitude does not alter the magnitude, magnitude of the speed of charged particle, magnitude of the speed, speed of charged particle, charged particle. Okay, magnitude of the speed of charged particle. So it does not alter the speed of charged particle. Okay, it only alters, it only alters, it only alters the direction of motion, the direction, it only alters the direction of motion, it only alters the direction of motion. Okay, so it means, hence, so this concept you need to know, the static magnet, if there is a static magnetic field that does not alter the magnitude of speed of charged particle, so it will not change the magnitude of speed of particle, it only alters the direction of motion, it just it alters the direction of motion. So it means hence the speed will be the same as it is as the one it started with, right? Thus which option is correct? So option A is the correct. Because speed will remain same, guys, because the static magnetic field does not change the speed. It only alters the direction of the speed, right? So option is the correct option. Well, guys, I'm going to stop here, and also, guys, I would request the student who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. And also, guys, share my lecture details with your friends, so that they will also be able to watch my free live lectures and will be benefited from it. Okay, guys, thank you so much. Bye now.